Let's continue to talk about the cell membrane and specifically the ion channels on it. So last time we discussed that there are this lipid bilayer, and there are a lot of channels on it. And some channels, those channels are like designed to allow specific ions to pass through. For example, you may have one sodium channel that only allows sodium to come in. Maybe you have one potassium channel that only allows potassium to move through. So I'm just drawing one direction, like either in and out, just as an illustration. But those channels allows ions to go either way. Now the question would be like, which direction would those ions go through the channels given any conditions? So this is what we are going to talk about, how to model the ion flux across ion channels. And this related to electrochemical potentials. Well, let's first think about what affects the flux. Now let me draw that again. You have lipid bilayer. This is extracellular space. And this is intracellular space. It's the same as cytoplasm. So now you may have a lot ions in and out, and maybe you have some concentrations outside and then some concentrations inside. For example, let's say this is potassium ion. So you have more concentrated inside of the cell than outside. So if there are channels allows those ions to go through, you may think, well, the concentration matters because like diffusion, although we haven't formally discussed diffusion, it will be in our next module. But from your experience, maybe ions will diffuse through the channels due to the concentration difference. So that's indeed the first impact of the direction. What we call is chemical potential. So when we talk about the chemical potential of ions, this is referred to the contribution from concentration difference. So this is not to be confused with the chemical potential of water we discussed earlier on. So those are two different things. So these are chemical potential of ions. Now let's see. We have a concentration inside of the cell. We call the Ci in, and the concentration out of the cell, like extracellular space, we call the C naught. Let's define the chemical potential difference across the membrane as delta mu. So this mu is chemical potential. We call it chemical potential. Delta means the difference across the membrane. This is approximated as RT natural log of C naught divided by Ci. That's it. This is the chemical potential difference of ions across the membrane. Potential difference across the membrane. Well, you may wonder how do we define the direction? Is it like the difference between in and out, or the difference between out and in? And there is no sort of like correct way to do it. It's usually a convention taken by anyone who choose to model the system. So in the expression I'm giving, in the logarithm, you can see that C naught is on the numerator and Ci is on the denominator. That means if C naught is larger than C in, so the natural log will be a positive number. then the delta mu would be positive. So in this case, then a positive delta mu means the chemical potential would allow ion to flow into the channel. So by writing this way, the convention is that influx of ions is considered positive. This is totally a convention. You can take the other approach. You can say switch the direction and you switch the sign. You are saying outflux is positive. It doesn't really matter. As long as you are consistent within yourself when you model your system, that should be fine. So for now, let's just assume ions move into the channel. So this is one contribution is chemical potential, which is basically this is a diffuse concentration difference. Now we know ions are also charged, so we know that there are chemical like membrane potential. So if you consider it as like an electrical circuit, then you have membrane potential. Even if you have same concentration, let's just hypothetically say you have some ionic species which like have the same like the amount like not amount the concentration inside and outside of the cell across the membrane. So there would be no contribution from chemical potential. However, based on their charge and based on the membrane potential, you know that if we are saying the membrane is negatively charged inside and then you may think about it might be positively charged outside. Let's just draw this as an illustration. Okay, so there is electrical field. Then if you have a cation, which is a positively charged ion, it will go into the channel, go into the cell. If you have a negatively charged ions, it may choose to moving out of the cell just because of the electrical potential across the membrane. So that means you need also to consider the contribution from electrical potential. So now we have the second contribution. Electrical potential is mu electric. Of an ion, this is referred to an ion, is minus Z F V N. Okay, I should mention that in the chemical potential of ions, let me define what is R. So R is 8.31 joule per mole per Kelvin. This is the ideal gas constant. T is absolute temperature. And then this electrical potential, this Vm is membrane potential. And then this Z is valence or electrical charge of ion. For example, the valence of sodium is plus 1. The valence of potassium is also plus 1. And the valence of chloride is minus 1. It's actually, you know what it means. Now this F this is 96485.3 coulomb per mole. This is Faraday's constant. You can see that by using this sign convention of electrical potential, that means I have a negative sign in front. And usually membrane potential is also negative. And that means if you have a positively charged ion, then it will give you the mu electrical potential will give you a positive value. And that will be consistent as our convention that influx is positive because a positive ion outside of the cell would like to move into the cell due to the electrical from the electrical field. Now let's figure out what's the units of mu chemical and the mu or dimensional, whatever you call it. For the chemical potential, we talked about in the first lecture of dimension. If you have a logarithm, the argument must be dimensionless. So that's why you see C naught divided by Ci. You always see a ratio if you are like in the context of chemical potential or concentration, if you see a logarithm, because you cannot have a quantity in the logarithm which carries dimension. That's not allowed. So you must have a ratio which gives you dimensionless. So that means the unit of chemical potential is determined by the unit of RT. So the unit of RT, let's see, we have R is joule per mole of Kelvin. Temperature is Kelvin. It gives us joule per mole. Now let's look at the units of electrical potential. So it's ZFVN. Z is a valence. It doesn't, it's just number, doesn't carry dimension. And F is FV. So Faraday's constant is Coulomb per mole. And the V we discussed in the last lecture, this is membrane potential, and the membrane potential is voltage. Voltage is, if 1 volt is joule per coulomb, so it also gives us joule per mole. So it makes sense that these two electrical potential and the chemical potential give us the same dimension. They are both energy per mole of material. And so if they are the same dimension, then they sort of physically can be like added up together or combined together to give you a new quantity. Especially if we consider the contribution from chemical potential, which is follow the gradient versus electrical potential, which is follow the electrical energy. And for ions across the cell membrane, and both are the factors that affects the direction of ion flow. So it's more about like which one is stronger, and you need to consider the sum of these. So indeed those are like energy. Oh, of ions. So now we need to consider the combination of these, which is we call electrochemical potential. Which is the sum of these two. So we have mu electrochemical RT naturally C not divided by Ci minus C F E N. So for specific ion species, so you may consider multiple ion species. So for multiple ion species, I mean you have sodium, potassium chloride, calcium bicarbonate, etc. Those are the electrolytes in and outside of cells. So for specific ion species, N is the index of the ion species. So the flux of this ion across the cell membrane is proportional to this electrochemical potential. This is how you model the ion channels. So this is the flux across ion channels. And the driving force, we always consider driving force. The driving force is the electrical chemical potential difference. So this is considered passive flux. Passive flux means you don't need active extra energy. For example, sometimes you may have active flux, those require like ATP, like extra energy to go against the chemical potential gradient. But for passive flux, you don't need extra energy. You just need to let ions go. You release it, it go naturally down the gradient of electrochemical potential. So the driving force of passive acts across ion channels are the electrochemical potential difference. It's the cell membrane. So when we say ion channels, this is a convention in the field. That you see the word channels, it means a passive channel, means for those channels, for those ion channels, they go through the electrochemical potential gradient. These are channels. For those require energies or other mechanisms, they usually call the pumps or transporters or exchanges, and we will discuss them in the next lecture. And channels are reserved for passive transporter mechanism. Okay, so this is how you determine the direction of an ion flux across the membrane. So usually you will be given what's the C in, what's the C out, and what is the membrane potential, and what's the valency. So if you know which ion you are talking about, then you know the valence. And R, T, and F, those are R and T R and F are constant, and the temperature is based on whatever the temperature is. So in general, as long as you are given the membrane potential and the concentration across the membrane, you will know which direction they flow. So you just plug in this equation and figure out the sign. So by our sign convention, by the sign convention, in this model, again, I'm just saying the sign convention that I'm using in my equation. Different people may use different sign convention. I cannot speak for everyone. Everyone is free to choose their sign convention. But for the sign convention we are seeing here in this model, if Jn is greater than 0, it means influx of ions. Influx means into the cell. Obviously, if Jn less than 0, it's outflux. Also, you can expect that when Jn is 0, no flux. That means it's a balance. So there is a balance between the chemical potential and the electrical potential. So the chemical potential and electrical potential are two factors. It's like a turbo war, like which one is stronger. Or maybe they just work together to help with the ion movement. For in some cases, both electrical and chemical potential would suggest ions to flow inside of the cell. Or in other cases, maybe chemical potential suggests that an influx, but the electrical potential suggests an outflux. Then the final direction is depending on which one is stronger. So the balance is like theoretically you can consider about it. In reality, it's usually going to happen. Like in physiological conditions, each ion is under some like non-balanced electrical chemical potential. But let's just say hypothetically, if it's in balance, what do we call it, or how do we quantify the situation? Or what does that mean if they are in balance? This leads to the next topic, which is called the Nernst potential. You may have heard about it in other contexts. Nernst potential. So it is known as the equilibrium potential. It's a theoretical voltage. So the Nernst potential is a voltage. It's a voltage across a cell membrane at which there is no net movement of a particular ion species. So it represents the balance point where the tendency of ions to move down their concentration gradient is exactly opposed by their electrical force pulling them in the opposite direction. So for this reason, you can derive the Nernst potential from the thermodynamic principle. Basically, it's the condition that the electrical chemical potential of the ions must be equal on both sides of the membrane. So this is let me rewrite it. This is the theoretical voltage across a cell membrane. So non-substantial is a theoretical voltage across a cell membrane at which there is no net movement of a particular ion species. So you can see it is ion species specific. Different ions have different inertial potentials. So when you talk about inertial potential, it's always referred to which ion do you refer to. Now let's see how it's calculated. It's just balanced energy. That means it is a voltage that you must have enforced that C. C. Sorry. Uh, in this, I needed to put a subscript Cn naught, Ci naught means the N species. Because this flux is ion specific. Okay, so for this species, we are requiring that you are at a membrane potential so that whether you when you're at a V and next. So from here you can solve for the next potential for the species number N. We just rearrange the equation. You get RT CNF log of C N naught divided by Cn in, Cn out divided by Cn in. So the next potential is species specific. Okay, let's have a look at an example to calculate the next potential so that you know how to use the numbers. So compute the next potential for potassium given the concentration of potassium outside of the cell is 4 millimolar, and the concentration of potassium inside of the cell is 140 millimolar. Solve it. So in this case, we are just going to use the expression for the structure. So let's see what is R. R is 8.31 joule per mole per kilogram. C. So usually when we talk about those biological scenarios, it means under physiological conditions, that means at body temperature, it's 37 degrees C. 37 degrees C is 310 Kelvin. And the Z, the charge of potassium is 1. The Faraday's constant is 694.3 colon O. And then you have a log of 4 millimolar divided by 140 millimolar. And if you put in these numbers, you will find that it give you minus 94.9 millimolar. That means you need to have a membrane potential to be that negative. You know, we just discussed that under physiological conditions, a regular tissue cell, it has membrane potential around the negative, like 60 millivolts. Now, minus 60 millivolts is not strong enough to balance the concentration difference of potassium. It needs minus 94.9, almost 90, minus 95 millivolts. So be that inactive in order to balance, because otherwise, if it's not that inactive, you can see potassium is highly concentrated within the cell. So the potassium, just by the concentration difference, like chemical potential difference, potassium would like to leave the cell. And if you have negatively charged inside of the cell, then the negative charge can hold on and grab them, and then they can counteract. So this is the amount of negative charge that and counterbalance the potential difference. Okay, let's look at exercise. Neuron 10 maintains the following and extracellular ion concentration. Body temperature. The sodium outside is 145 millimolar. Inside is 15 millimolar. And for potassium, the outside to 4 millimeter. And the inside is 140. If the membrane potential is given, so if the membrane potential is Vm equals to minus 70 millivolt, determine the electrical potential for each ion. Electrochemical potential for each ion. It actually means the electrochemical potential difference for each ion. Which ion has a stronger driving force into the cell? And again, which stronger driving force into the cell? That's all for this lecture.